All right, everybody. So we are down to the end of the semester. We are now ready to do our hypothesis tests for two variables at a time. So we're trying to figure out if there's an association between two different variables, which basically means that values of one of the variables seems to be associated with different values of other variables. So I'm going to use this particular example because we're doing ANOVA. Analysis of variance is what ANOVA stands for. And what ANOVA is for is when you have a categorical variable as your explanatory variable and a quantitative variable as your response variable, you're looking to see that if for the different categories of your categorical variable, are the averages in the quantitative variable different? And so in this sample, we can see that they're different. So people who don't wear glasses or contacts, on average in our data set, have 3 siblings. And it gets lower and lower and lower as you go into these different categories until you get down to the people who just wear contacts. And it looks like they have fewer than 2.5 siblings on average. It's not that any individual who wears contacts automatically has fewer siblings. When you look down here at the side-by-side box plot, you've got somebody here who looks like 11 siblings, and then folks over here that are only kids, right? They don't have any siblings at all, but you're looking at averages. And so what we're trying to find out with a hypothesis test is assuming that in the population, there's no difference at all between what the average number of siblings is between these two categories. It doesn't matter. We're assuming in the population, it doesn't matter what you wear for eyeglasses, your number of siblings on average is the same. And once we assume that, we're seeing if this difference in our sample is different enough to be too rare to be believable. So it's very similar to what we did with our hypothesis test with a single variable, where we said, I'm going to assume the mean or the proportion is this, and then I'll look at the mean or the proportion of my sample and see if it's far enough away to not be believable. You get that p-value that is that criteria or criterion that really sets whether, I've got enough evidence to think the null hypothesis is not true, or you know what, I'm thinking that I have enough evidence. I don't have enough evidence, and maybe that is true. Okay, so I'm going to go to my slide to show how to set this up, and then we'll get back to the Python. But really, I'm expecting these means are different enough. And ANOVA stands for analysis of variance, and the reason variance is in there is because depending on how much these categories vary and how many siblings they have, that's going to enter into it as well. If these are super, super tight and no variation at all, then you would expect that a difference that shows up between these two categories is really a big difference, because how would we get such a difference if all the numbers are close together? On the other hand, if the numbers in your categories are super far apart, like kind of these are, then you're like, well, maybe randomly we got something that was down here instead of up here. So variance and means are both used to calculate the p-value in this case. But luckily, Python does that all underneath the hood. We don't have to analyze any of the analysis. We just look at the bottom line. What's our p-value like? Is it less than 0.05 or not? Okay, so on my slide, I'm starting with kind of a summary of what we're testing. And because my two variables are number of siblings, or sibling count, is my response variable. That's my quantitative variable. And eyewear is my explanatory variable. So we're testing whether the average number of siblings is significantly different among these different categories of eyewear. So our null hypothesis is that in the population anyway, it doesn't matter which category I'm in. All the average number of siblings are the same. So this mu is standing for the population average number of siblings in eyewear category 1. That's equal to the population average number of siblings in eyewear category 2. So these symbols, even just these symbols put together, both of these variables, because the mu is talking about the average number of siblings, so the quantitative variable, and then the subscript is talking about a category in my categorical variable. So if you're doing this particular null hypothesis, then you have to have as many categories as you have. So I only have 4. Remember, in my categorical variable, I just have 1, 2, 3, 4 different categories. But so maybe this is mu1 and mu2 and mu3 and mu4. But if you have more or fewer categories, then you'd have more or fewer of these mu's in here. So the alternative is that they aren't all equal. So it's not specifically saying which ones aren't equal to which ones in this alternative hypothesis. We're just saying, hey, the null hypothesis, they're all equal. When we look at the sample, is it enough evidence to show that, no, they're not all equal? At least 2 of them are different from each other, most likely, based on the statistics. Okay, so in Python, the way this is done is kind of labor intensive. So you start out doing the hypothesis test, and so it's got a few lines here. You particularly this first line is complicated because first off, you have to import the stats model as SNF. Okay, so that's this, and then this formula. So formula equals, and you got to make sure that you put your response variable, your quantitative variable first here, and then a tilde. So I use shift and then the key on my keyboard right next to the 1, a shift backtick is the tilde. So my quantitative variable is sibling count, my categorical variable is iWhere, and I put in here as the formula equals, quote, sibling count tilde, capital C parentheses iWhere, close parentheses, close quotes. That's a lot. So it's the quantitative variable that I know is our output variable. That goes first, then tilde, and then with a C attached to it, your categorical input variable. Then you tell it to fit this model and get some results. And then the results that you're printing is all this stuff. And it's a lot. The good news is we don't have to really analyze most of this. There's a lot here, and we don't have to really worry about it. What we're going to worry about is our F statistic. So this is similar to our T-score or our Z-score when we did the one variable hypothesis test. And this is pretty darn big. So, we're used to things like, 1 or 2 or maybe a half, not being very big. Well, this is pretty big. How big is it? Well, the probability that I'd get a F statistic out of all this data, that's 9.984 or bigger. Well, this probability is really low. It's 1.47 E minus 6. Or another way to say that, 0.000000147. So definitely less than 0.05. So we have significant results. So already, just with that, there's enough evidence to support that not all the means are the same. Like p-values less than 0.05. So enough evidence to show that not all the means are the same. Unfortunately, or maybe fortunately, depending on what you're trying to figure out here, we're not done. And the reason we're not done, and maybe I should have stuck back here, is not all the means are equal, but which ones aren't equal to which ones? So there's something called a post hoc. So post just means after. So after you've run the test, if you have significance, if you really have a p-value that's less than 0.05, so you have significant results, then you go back to do some more coding to figure out which categories are significantly different from each other, which are so different that we think they're different in the population maybe. So when I'm looking up here, I'm thinking maybe the contact lens category and the neither category, right? These are really far apart, and maybe not the neither versus the eyeglasses or the both versus the contacts. I don't know, just looking at it, but it just seems like these are so far apart. Plus, this isn't that spread out. So since it's kind of tight in its standard deviation, it's even more shocking that that you would have something so far an average just by chance, right? So anyway, the post hoc, what it does is it pairwise compares. So this post hoc is starting right here. We now do the post hoc, it's called Tukey, the post hoc Tukey test to see which pairs of eyewear categories have significantly different average number of siblings. So out here, what I'm doing is I'm setting up with a subset of my data frame. The DF data frame has all the variables in it, plus the ones that I've created and data managed and stuff. I've got a lot of different variables. What we're doing is we're getting a subset that's just the sibling count and just the eyewear, and we've dropped the NAs. So this is important to not get an error to make this subset of your data frame. Once I have sub 1, I can use it just like I use DF. That is, I could say, oh, well, within these two variables, I could go sub 1 bracket parentheses sibling count and just look at sibling count, for example. But I don't have anything else in the data frame, and I've dropped the NAs. This is the important part, is that I've dropped the NAs. Then I have to import this stats model, stats multi-comparison is what that stands for, as multi. And then these next two commands that I'm showing is not necessary. You don't need to do this in order to do the Tukey post hoc test. I'm doing it because when I looked at these graphs, yeah, okay, this is about 3, and this is about 2.5 for these means. And okay, this is more spread out than this. But what I thought I'd do is show you how to see the actual means of the sibling counts for each of these different categories so that I can see them. Here's that one that's about 3, and here's that contact lens mean that was about 2.5. I can see what that numbers actually are. And I see the standard deviations, the STDs, for these different categories, the standard deviations of the sibling counts in these different categories. And notice that just what I saw on that side-by-side box plot, the contact lenses aren't as spread out. Right? The one that's the most spread out is the neither category. All right, so that sort of gives some justification for what we see when we do this Tukey. So there's, again, 3 lines, and the order that you do this stuff is important. So again, the quantitative variable comes first, and the categorical variable comes second. And notice instead of DF, I'm using sub 1. But once I have that MC1, then I just say, hey, do the Tukey on that, and then print these results where you've done the Tukey. And what it does is it takes all the different combinations of pairs of categories. It puts both with contact lenses, and then both with eyeglasses, and then both with neither, and then contact lenses with eyeglasses. Out of those 4 categories, it kind of puts them together in pairs in all the different ways that that's possible with those 4 categories. And then it shows you these adjusted p-values. And then I don't even have to compare these p-values to anything. I mean, I can see that this one is super small and this one is super small, and that these aren't as small. But I don't even have to do any comparison. It tells me whether I should reject the null hypothesis or not. So the only categories where I would say, yeah, we have enough evidence to show that in between those 2 categories, the means, I have enough evidence to reject that the means are the same or support that they're different. Contact lenses versus eyeglasses. Contact lenses versus eyeglasses. We had significance. Those are different enough in the sample. And then here's another true contact lenses with neither. And that was the one we were speculating about originally just by looking at the graph. Okay, I know it's a lot. Good news, I'm going to show you this on the video. Good news is no con. The only con you have to do now for the rest of the semester is catch-up con. So cool. We're just going to be setting up to do our final exam. And I guess I lied. There is one final con. It's an exam. It's kind of looking at the whole semester of stuff. So, I'm hoping that we have some time to practice old con sessions so that you can do that. But basically, we're setting up for your presentations. All right. I'm going to shut up. It's at 15 minutes. So I'll talk to you in class. Bye.